Well, hello class. You're not here. So we're going to do experiment 9, or I'm going to do experiment 9, and let you work through the calculations, and hopefully it's all going to make sense. So what we're doing today is we're going to determine the KSP of calcium iodate. Now, as we know, we want to set up our KSP expression, and the KSP would equal to the concentration of calcium ions times the concentration of iodide squared. We're going to determine the iodate concentration using titration. And once we know that, we'll figure out the calcium concentration and then calculate the KSP. We're going to be doing something very similar to what we did back in experiment 2, where we're going to be combining a couple of different reactions and using starch as our color indicator. We know that iodate reacts with iodide and acid to form iodine. That iodine will then react with the thiosulfate, which we're going to be using as our titrant. And when all of that iodine disappears, then the starch solution, which will be blue in the presence of iodine, will turn clear. So starch will be our color indicator, the thiosulfate will be our titrant, and we're going to be combining iodate, iodide, and acid into our reaction flask. So again, once we determine how much thiosulfate we need to titrate, we can then convert that into moles of iodate and then molarity of iodate and get to our KSP. We'll work through all the calculations later after we finish our titrations. Okay, everybody, we're back, and we're going to do our first trial now. You've set up your burette. Make sure you've conditioned your burette 3 times, and when you've done that, make sure there's no air bubbles in your burette tip. Now I've got about 50 mils of DI water. The exact amount doesn't matter. I've weighed out about 2 grams of potassium iodide. I will add in, and we're going to make sure that completely dissolves before we do anything else. Just give that a good swirl. There we go. Next, we want to add 10.00 mils of our saturated calcium iodate. Now, I've already rinsed and conditioned my pipette. So we'll go ahead and transfer 10 mils. And we're going to go drawing our liquid into our pipette. Just past it, and we'll try to, oops, a little too much. Got to draw a little bit back up. There we go. 10.00 mils, and we'll let this all drain into our flask. And as I'm letting this drain, I'm just going to sit and wait for a few extra seconds here to make sure any of that extra liquid can drain down the glass walls, the inside of the pipette. And you'll usually see if you wait, 10 seconds or 15 seconds, you'll see 1 extra drop or so come out of that pipette. Put my lid back on my calcium iodate. We need about 10 mils of HCl, and again, HCl is in excess. That's one of our excess reagents. So it doesn't matter exactly how much we add. If you add a little bit more or a little bit less, that's okay. That's pretty close to 10. That's good enough. We're going to add this, and now when we add our HCl, the solution is going to turn kind of that burnt red, kind of brownish, orangish brownish color. You're talking to the colorblind guy trying to tell you the color. You can see it. Next, we want to add our starch, which we're going to use as our color indicator. And we want about 5 mils of starch. So, there we go. And again, it's a color indicator. It's not quantitative, the amount that we add. And when we add our starch, our solution, will turn that dark deep blue color. So there is our solution that we're going to titrate with all of our reactants. Now I've recorded the temperature of our calcium iodate. We're at 20.8 degrees today. My initial volume of thiosulfate happened to be right at 3.00. Again, we don't want to set it to a specific number. I just drained a little bit through my tip, and that's what I saw for this particular titration. And what we're going to do now is we're going to titrate until the solution turns clear. I'm going to start going fairly fast because I know it's going to take more than 5 or 10 milliliters. And I'm going to get to a point here, I'm going to swirl and I'm going to start slowing down a little bit. And we want to get to that point just where that deep blue disappears and our solution turns clear. Whoa, I started seeing a little bit of clarity there. There we are. So that one probably went just a hair too far. What we're going to try to do is get to where we get 3 good, consistent trials. So that now puts me in the ballpark, and this turns out to be, okay, that's about 17.03 milliliters. Now, my other trials may come out a little bit less than that if this was a little too quick and dirty, but I'm going to keep going until I know I have 3 consistent trials, and they should be within maybe 1/10 of a mil, or maybe a little bit more than that, but they should get 3 trials that are all really close. So I'm going to go ahead and finish those trials, and then we'll come back again in a few minutes. So we're back. I finished the titrations for part 1, where we were titrating our calcium iodate in pure DI water. And now we're going to do the second part, where we're going to titrate our potassium iodate in 0.01 molar potassium iodate. So since we're spiking up and there's going to be extra iodate in solution, that's what we're titrating against. So it should take more thiosulfate to titrate. Let's see if that works. So I'm expecting it'll be more than about the 15 mils that it took for the first 3 trials with pure DI water. So I'm going pretty fast for that first 15 mils. Now I need to slow down a little bit. And what should happen as I start getting close, I should start seeing a little bit of clearness showing up in my flask and then going back to that dark blue. Just like when we did our phenolphthalein, we started to see a bit of pink and then that pink disappeared. It's just like that, but the opposite, where we see a little bit of clearness, but then it goes back to dark blue. And if I do a good job this time, what I'll start seeing is getting a little bit turning into a light gray, or I'll start seeing that dark blue get a little bit lighter and lighter as I get close to that endpoint. So I'm just going by small aliquots here. I'm close to about 19.5 mils. Yeah, I'm starting to see it get a little bit clearer. Ooh, it's looking less dark blue and a little bit lighter. Oh wow, that's really close. I have a light blue now. And so I'm gonna spin it. And there it is. I went from that blue to clear with just the smallest amount that I could deliver. So I'm going to read my burette volume. I'm going to do 2 more trials, and then we'll come up, wrap up, share the data that you're all going to use for your calculations, and go through some of those calculations. Okay, you guys still aren't here, so I guess I'm going to have to wrap up. So for our calculations, here's the data I collected and I want you to use for your trials. I got rid of that first trial from part A because I overshot the endpoint. I feel pretty good about my other endpoints though. There you go. So for our calculations, for part 1, we're going to determine the iodate concentration for each trial, and then calculate the average iodate concentration. From there, we can calculate our molar solubility and KSP. Part 2 gets a little bit trickier because we have that common ion effect. After we determine our average iodate concentration, we want to figure out how much of that actually came from dissolving our calcium iodate. Then we'll calculate our molar solubility and KSP. For your discussion, you're going to calculate your percent air, compare your molar solubility results from part 1 and 2, and compare your KSP values from part 1 and 2. Comparing these values means not just listing your results, but also explaining them and whether they make sense or not and why. Make sure that you would do this all in a complete paragraph with complete sentences, and there should be no further calculations in your discussion section. You're just explaining the results that you found. Okay. For our calculations, for the first part, we're going to determine the iodate concentration starting with our volume of thiosulfate we used. Knowing the molarity of thiosulfate will convert to moles, and then stoichiometry can convert to moles of iodate, and then using the volume of iodate that we pipetted in, or the 10 mils, we'll get our concentration of iodate. And we're going to do that for each trial, and then get the average for our trials. Once we know the concentration of iodate, we know that calcium is 1/2 of that concentration, because all of that iodate came from dissolving calcium iodate, and the same is true for the calcium ion concentration, and this is just a stoichiometry. So we can easily determine the calcium concentration as 1/2 our iodate concentration, which happens to be our molar solubility, S. And then we can plug into our KSP calculation, our calcium concentration times our iodate concentration squared gives us a KSP. Part 2 gets a little bit trickier with our common ion effect, and we have to account for that. We're going to determine the iodate concentration just like before, and the average iodate concentration. But now, in our ICE table, we have to account for that common ion, the 0.01 molar solution of iodate. The molar solubility is S, so we get S amount of calcium and 2S amount of iodate that dissolves, resulting in our final or our equilibrium concentrations of S and 2S plus 0.01 molar. We want to know how much of that iodate is coming from the dissolution of calcium iodate. So we're going to solve for S. We take our iodate concentration that we calculated from number 1, or actually number 2, our average iodate, and that's going to equal 2S plus 0.0100. Solve for S, that's your calcium ion concentration, and that's your molar solubility. We can now plug in and solve for KSP. I think the most common error that I see is putting in the shortcut of 4S cubed for KSP. But don't do that, because the iodate concentration isn't just 2S. It's the 2S plus 0.010 molar iodate. Make sure to plug in the actual concentrations that you found for both calcium and for the total iodate concentration. Again, we're accounting for the total concentration of iodate and the total concentration of calcium in KSP, because those are in equilibrium with the solid calcium iodate. And that should do it for your calculations. Hope this has been as much fun for you as it has been for me. Good luck, and tuning out until we do our next lab.